Okay, so I led into this example in the last video. We're going to actually do it now. We're going to start off by finding the equation of this line segment. It looks like it crosses right there. You know, what is that? Is that 4.5? I'm not really sure. So it looks like it might cross at 4.5, but we're not sure. You should be sure. Don't guess with something like that. So in order to do that, we're going to find the equation of this line. So the slope would be 3 minus -1 over 3 minus 5. So what's that? 4 over -4/2, which gives us a slope of 2. Oops, -2, sorry. And there's a point. So let's see. Find the equation of the line segment. Y equals 3 minus 2 times x minus 3. It says use it to find the x-intercept of the graph. The x-intercept would be when y is 0. I guess I'll expand that. 0 equals -2x plus 9. So solving this, 2x equals 9, x equals 4.5. Exactly what we thought, but now we're sure. This is crossing at, right there, at 4.5. Good to know. All right, so now we're going to evaluate an integral. All right, from -7 all the way to 0. So we look at those pieces. This part is negative. It's a triangle. Looks like the area of that would be given by 1/2 times the height. Looks like 1. And the length, 7 to 2, negative 7 to -2 would be 5. So this would be, -5/2, because it was underneath the x-axis, plus the area of this quarter circle here. So that would be 1/4 times the area, pi times 2 squared. So I guess that would just be pi. I gotta clear some of this out of here. It's driving me crazy for the next part. Okay, this time we're gonna find we're evaluating the integral from 5 all the way to 2. So we're going backwards. So remember, the signs are the opposite of what they think you are. We have this one little triangle below and this bigger triangle above. The triangle below would be 1/2 times 4.5 to 5 is 1/2 times the height of 1. Remember, that's positive. Then we're going to subtract the area of this second triangle, which would be what, 1, 2.5, so 5/2 by 3. Okay, and we have numeric answer, so there we go. All right. So far, everything we've looked at has been nice, continuous, smooth, maybe a point here or there, but it was nice graphs. Okay, these are integrable. All continuous functions are integrable. So if a function is continuous on a closed interval, then it is integrable. Okay, if it's not integrable, that means it's not continuous. All right, so let's look at a function that is not continuous. Senor Salta, I'm sure you remember that, right? Looks like this. It's jumping from -1 to 1. We're going to evaluate this integral from -2 all the way to 3 by graphing it and using areas. What shape do you see? Well, that would be a rectangle, and so would that. The area of this rectangle is 2 by 1, or 2. The area of this one's 3. Now, checking the direction that we're traveling, we're going forward, so we're going to have -2 plus 3, so that would be. So just because a function is not continuous doesn't mean that we can't find the integral value of it. Okay, sometimes you don't see functions in graphical or in an equation in algebraic form. We can find areas, though, if we just have a numerical expression as well. So you got to be really careful. Look for important things. F is a continuous function, which means it's integrable. Oh, another important thing. Why would they say this? F is always positive, or it's non-negative. That's a better way to say it. It's non-negative. And we have selected values in the table. Now, being a trained math teacher, I see 0, to 0.5 to 1 to 1.5 to 2 to 2.5 to 3. Those are all nice equal jumps. We don't always see that. I'm just checking out that table down below. 0 to 1, 1 to 3, 3 to 6, 6 to 6.6. Okay, so that one, something weird's going on there. Let's focus on this nice happy one first. All right, approximate 0 to 3. So we're going to say, hey, 0 to 3, this integral, we're going to approximate you using numeric methods as indicated by the data. So we're going to try to figure this out. Now remember, it's non-negative. So area is the same as the integral. Oh, I just answered part B. Yes, the integral approximations could represent approximation of the area because f is non-negative. So we can use a left Riemann sum. If we're going 0 to 3, we can use, let's see, 1, 2, 3, 4, 5, 6 different rectangles. And we can do that by saying each one's 1/2, and the heights would be given by the left endpoints, 2 plus 4 plus 6 plus 7 plus 4 plus 1, whatever that is. Okay, or we can approximate it by a right Riemann sum. In this case, we would use the right endpoints, 4 plus 6 plus 7 plus 4 plus 1 plus 5. Or we could also do a trapezoidal approximation. I'll write that one. Oh, actually, we could do one more, can't we? For the trapezoidal, we can just add these up and divide by 2. But we can also do a midpoint for this one. We can't always do that. Okay, but see, we have the midpoints of different values. We have the midpoint of this, we have the midpoint of this, and we have the midpoint of this. So we could use a midpoint approximation as well. But this time, we can only have 3 instead of 6. So we have 4 plus 7 plus 1. All right. So let me get this out of here. Blah, blah, blah. See, we approximated them. I could get decimal values, but I want to save your time. Last thing we're going to do with this table is approximate f prime of 1. All right, let's get these things out of there. Now, when I see 1, that's right here. I could use these values. I could use these values. Okay, I could use those, but it's getting a little further. I'm going to choose to use those. Okay, and I'm going to show the difference quotient there. 7 minus 6 over 1.5 minus 1. So that's 1 over 0.5 or 2. Like I said, I could have approximated it using 0.5 to 1. It would be a different number, but that's okay. As long as you show the difference quotient, then I understand what you're saying. All right. And probably the last one. What else do we have on here? Yeah, we'll save that for the next video. The last one we're going to look at today is a table. Another table. This one's different. I already told you. Not even jumps. It's going small, then big, then really small, then bigger. Okay. But it is a continuous function, so which means it's integrable. So we're going to approximate this integral from 1 to 8 using numeric methods, just like we did before. Now I noticed that this is 1 and this is 8. So who cares what's happening at the end? Get rid of that data. Don't let it confuse you. All right, so we're going to go from 1 to 8. So it looks like we can do this with 4 rectangles using the left-hand side. So for this first width, it's 2. And the height is 3. The next one, the next width is 3, and the height is 3. Okay, the next width is 0.6, the height is 1. And then we have, what's that, 1.4 times 5. If this is confusing to you using a table like this, it's only going to take you a little bit of time to sketch a quick graph of this function. You know, plot the values 1 to 8, 2, 3, 4, 5, 6, 7, you know, and try to just put values. So that's 3, this is 1, 5. I picked the wrong numbers. I was going even spacing, but you get the idea. Draw a little graph. It won't hurt you to do this. All right, so I did a left Riemann sum. I guess I'll do a right Riemann sum as well. So this time, I'm going to use that same width of 2, but I'm going to take the right-hand height, 3. And a width of 3, and a height of 1. A width of 1.6 and a height of 5. And a width of 1, I said 1.6, that was just 0.6, sorry about that. 1.4 and a height of 8. I can also do a trapezoidal approximation using these values. Okay. I can't, however, do a midpoint. I don't have any midpoint values, so that's not really going to help. I'm going to clear this stuff out. And let's discuss this. Could any of these approximations represent the approximate areas of the region? And this answer is no. We don't know. Because we didn't know if this function, it's going from 3 to 3. Did it drop below the x-axis? Did it just stay constant? Did it go up or down? So we don't know the signs of this function. We don't know that it's non-negative, so we can't assume that it represents the area. All right, and then the last thing that we'll do with this table is approximate f prime of 7. 7 is between those values, so that's what we're going to use. We're going to say that's 8 minus 5 over 8 minus 6.6. All right, we could get a number, but why? This is a numeric representation. I would only try to get a more simplified expression if you needed to use this value in something else. All right, so that looks like a good place to stop.